All right, guys, we got going to start acceleration. So it's a continuation of motion. This time we're going to talk about changing motion. The equations are here. I'm going to come back to those later in the slides. All right, so what's acceleration? The book definition's right there. It doesn't mean the most, but it's the rate of change of velocity. That's the physics definition, right? Rate of change of velocity. What does it mean to change your velocity, right? It means to speed up, slow down, or change direction. It's all three things: speed up, slow down, or change direction. And it's how quickly you do that. So the quicker you speed up, or the quicker you slow down, or the quicker you change direction, that's acceleration. And then can you feel acceleration? Yes, right? You can feel all of those. Speed up, you can feel it. Slow down, you can feel it. Change direction, you can feel it. And then well, sorry, no, let's jump to the comic. So you got, like it says, normal people see a steering wheel, a brake pedal, and a gas pedal. Because of the way we define acceleration, those are all accelerators. So then the physicist sees accelerator, accelerator, accelerator. Um, so silly, but because it's defined as speeding up, slowing down, or changing directions, those are all accelerators. So when we say, can you accelerate to a stop? It sounds funny, but yes, you can accelerate to a stop. Even though we would say decelerate, right? You would decelerate to a stop and you would accelerate to a higher speed. With physics, we can say, I can accelerate to a stop, I can accelerate to a higher speed, I can accelerate to change direction. So we don't need the extra terminology. It does exist, but we don't necessarily need it. This is the equation here is just the formal definition of it, and it's how we derive what we'll consider the third equation. But A, again, with the bar over it, is average. So that's average acceleration. The delta's change, and then V is velocity like it was, and T is time like it was. So delta change means VF minus VI, so it's a change in velocity over a change in time. If we solve for VF, so if you do a little algebra with the manipulation of the equation, you get VF equals VI plus AT. That's the equation that's the one both are on the equation sheet, and both are in the note sheet. So it's either whichever one you want to, whichever version of it you want to use. I think VF equals VI plus AT is the one that pops in my head, but that's just me. Um, Units, real quick. So our units are weird. I mean, there are units, but we don't typically say acceleration is one number. We say 0 to 60, like it says here, 0 to 60 miles per hour in 4 seconds. Like you see a commercial, you read up on a car, like what's it 0 to 60 time, stuff like that. That's how we give acceleration: 0 to 60 in 4 seconds. If we were to plug that into the equation, that change in velocity over change in time, right? We get 60 minus 0, so that's a change in velocity of 60 over 4 seconds. 60 divided by 4 is 15. Here's where the units come in. It's 15 miles per hour because that's our speed velocity units, right? Divided by time, which is in seconds. So we get 15 miles per hour per second, which means every second your speed increases by 15. So in 1 second you're going 15, 2 seconds you're going 30, 45, 60. You get it. Just keep adding 15. The metric system is a little more straightforward. It's meters per second per second. You still have the same type of idea, right? Distance over time, and that's acceleration. So for the metric system, because we have meters per second, we can shorten that to meters per second squared. So when we're doing problems and you see meters per second squared, you should know that's an acceleration. When you see meters per second, that's your same old velocity. So real quick, just the difference though, 10 meters per second means your position is increasing by 10 meters every second. So 10 meters, 20 meters, 30 meters. 10 meters per second squared means your velocity or speed, how fast you are going, increases by 10 meters per second every second. So 10 meters per second, 20 meters per second, 30 meters per second. Just be cautious. You see that square, it's an acceleration. What happens when you change acceleration? So is there a change in acceleration over time, like a rate of change of acceleration over time? There is. So going back, what we're going to study is constant acceleration. So you hit the gas pedal and you just gradually increase your speed, or you hit your brake and you gradually decrease your speed. Where you're going to change direction, you're just going to do it at a constant acceleration, gradual, steady, I guess is a better word. But what happens if you don't do that? We call that a jerk. And you can picture this: hit the gas pedal, hit the brake, hit the gas, hit the brake, or hit the gas, let go, hit the gas, let go. Like you'll get that jerking motion. That's what we call a jerk. And then here, you don't need to know derivatives, but anybody doing calculus, if you take the derivative of position, that's dx over dt. That's velocity. If you take the second derivative, so d2x over dt, you get what we call acceleration. And if you take the third, if you do a derivative one more time, so the third, you get d3x, like it says here on this shirt here, and it says don't be a jerk. So it's a silly little comic for the calc people out there. We don't need calculus. We're just doing constant. We don't have to worry about derivatives, that kind of stuff. Class K, problem side one. You're gonna come to this later in the week, but so it's the moving man simulation. I'm sure some of you dread this guy. We're almost done with him. The directions are on the slide. I just want to point something out. Don't go. So the question we're trying to answer is how can a negative acceleration cause an increase in speed? So you're going to play around with the sliders. I wouldn't max it out, right? You can go like just don't max it out. If you max it out, it's hard to tell his motion. You can look at the numbers. You can actually look at his motion, and you'll see if he's increasing speed, decreasing speed, or staying the same. And then that's all it's asking for in that activity. The accelerometers. Um, oh, here, sorry. We'll come back to the accelerometer. So here, you guys are gonna get to it later, but I'm gonna talk about a little bit now. I'm gonna give you the pattern, and then it's still verify it. You should see it. I mean, it should be obvious to you. What is needed for constant velocity is just no acceleration. What's needed for speeding up, the direction you're going, the signs for the motion and the acceleration need to be in the same direction. So you can be going to the left and speeding up, and you can go to the right and speed up. What is needed for slowing down, they need to be opposite of each other. So if you're headed to the left, your acceleration would be to the right. And then how can a negative acceleration cause an increase in speed? If I am going in the negative direction. So typically we will define negative as left. If I'm going to the left and I accelerate to the left, I am going to speed up. And then that's you're going to verify all that with the problem slides. Measuring measuring acceleration real quick. So in class we use the motion detectors. Uh, if you're at home, you're going to be doing the simulations, which is fine. I just want to give you a rundown. We can measure acceleration. One is with a motion detector, and it sends out a sound wave, an echolocation thing, and we can determine where you are based on that graph. The other way, and this is an option you guys have at home, is your phones. Your cell phones have a chip in it that it knows when you tilt it, right? You can tilt it left, right, whatever, up, down, reorient it. There's an acceleration sensor in there that can pick that up. Now, how did we measure acceleration before all this technology? Was a silly little, we hooked a washer to the string. You can still make this if you want. You hook a washer to a string. This thing will detect, it'll move with whenever you accelerate. So going at a constant speed, it just hangs there like normal because there is no difference between constant speed and being at rest. But the second this car accelerates, uh, it'll tilt. And we can measure that angle. This is how we did it before tech. When we get to forces, probably we'll do some force analysis. I don't know that we'll get to the specific one, but we'll see how far we get. All right, equations and problems. Let me see if I can move this out of the way. All right, so the three equations on the left here, these are the basic definitions. Here's the definition of velocity, here's the definition of average velocity, here's the definition of acceleration. From these three equations, we can derive the three equations over here on the right, and these equations are the ones we're going to be using. These are the equations we're going to focus on. We still have the constant motion, the still v equals u over t. So if you're doing a problem and they never mention acceleration, um, you know it's v equals d over t, or you have to find acceleration to get it. So I'm going to go through these equations real quick. Delta, and you've seen all the variables. There are 5 possible variables. There's VI, VF, those initial velocity, final velocity, acceleration, time. And I'll cover all this when we're doing the problems. This is just a quick, kind of quick overview. But the distance here is going to be the initial velocity times time plus 1/2 AT squared. And I was going to say, oh, yeah. So if acceleration is 0, if there is no acceleration, then d equals vt. You get the same. You get v equals d over t, just in a different format. Here, now we got vf squared. So you take the final velocity squared equals vi squared plus 2ad. If a is 0, all it's telling you is that vf squared equals vi squared, and which is v, right? If you're not accelerating, then your initial has to equal your final. Same thing with the last one here. The vf equals vi plus at. Well, these are the three equations we'll use, and I'll show you this in the problem sets, but what what what's the big deal about having three? Well, if you look at this first equation, d equals vit plus 1 half at squared, there is no final velocity. There is no vf. So instead of finding vf, well, so I'm sorry, let's take a step back. If you're doing a problem and you write down d, vi, t, and a, and you never write down anything about final velocity, the problem never says anything about final velocity, doesn't mention it at all, then you know you should use this equation because the other two equations have VF in it. And so you could use those equations to get VF, but then you're going to have to do another equation to get whatever you were looking for up here. So there's typically, for most of the problems, we will always be able to solve them in one equation. We are going to get to projectiles, um, where we're going to be throwing stuff, shooting stuff, that kind of thing, and you'll have to do those in two steps typically. But that's future. This one, the VF squared equals VI squared plus 2AD. There is no mention of time. So if you're doing the problem and you write down VI, VF, A, and D, and you never write down time, then you should use that equation. Now your brain's going to say, "Oh, I'm missing time. I need to find it." And then you're going to use another equation to get t, but you don't have to do it that way. It's not wrong. It will work. You can get t from another equation, then plug it back into the equation that you needed it in, or that it was missing from. But it's just extra. It's an extra step that you don't have to do. And then last one, VF equals VI plus AT. This one is missing uh, displacement. So if you're doing a problem and it never mentions anything about how far you went, then use this one, VF equals VI plus AT, because the other two equations have how far you went in it, and you would have to do extra work to find that out when you could just do it in one equation. Again, not a right or wrong thing, just a quicker thing. And then we'll come back, like I said, later in the week, you guys are going to see the problem sides. And the lab real quick. So definitely message me if you got questions. I'm gonna run. I don't know that yours will take. The sim probably is a little quicker than 60 minutes. Um, Math review. So, all right. First thing. So one of the questions is going to ask you to find the acceleration uh, from the quadratic. So it's going to be a little confusing. The lab is written as if you've never seen any of this before, which is probably true. Uh, so I've written it step by step just so you can kind of, it's more of a like how to do it. Um, and then we'll use that in future labs. But there's one way to analyze or to get acceleration from a position time graph like you see down here, and I'll talk about the graph here in a second, is with the quadratic, right? So if your graph curves, you're accelerating, right? Your position is changing quicker than the time, and you're accelerating. You're speeding up in this case. If it flattened out, then you would be slowing down. In this case, though, c is increasing. It's a increasing speed, so the slope is increasing. It's getting steeper. So how we find the acceleration? You're going to see this in the lab, so I'm just kind of overviewing it, not giving you full details. But y equals 1/2. One of the problems you're going to have to uh, solve something like this, where you have y equals 1/2 x. And then what is x if y is 4? Well, if y is 4 and I want x, I should divide both sides by 1/2, not multiply both sides by 1/2, which is what most people do. You got to divide both sides by 1/2. So 4 divided by 1/2, you're going to get 8. A lot of people will write 2. If you're just looking at it real quickly, your brain's like, oh, that's 2. So take a second, write it out. It's not 2. You're actually doubling it because you're dividing by half. But and so when you're doing the lab, which graph best represents an acceleration is Charlie. We've seen that a couple times now. B would be if you're uh, going in a constant speed, constant velocity, right? You're going away from the the moving man guys going at a steady speed. And then A would be if they're not moving at all. And again, we've seen this a couple times now, but this time we're going to actually use it to analyze stuff. So not the most exciting lab, but good for analysis. The doodle review. This is more an in-class thing, but I will still do it as a review. You just don't have to draw it out if you don't want to. Um, so sketch each graph. Here, move me again. All right. So all three of these represent acceleration. So here, we'll start backwards. And we're always going to do constant, steady acceleration. So if you were to graph that on an acceleration graph, it would be this straight horizontal line. So if your acceleration, let's just say it's 10, you're always increasing by 10 meters per second, 10 meters per second, then you're going to get a constant velocity. And on a velocity graph, that would be over 1, up 10, over 1. Again, I'm just making up numbers, but they would all be the same. Over something, up 10, over something, up something, over something. It'd always be the same something. Uh, Now, because your velocity is increasing, that means your position, right? Every second you're going your speed's increasing. So you're going 10 meters per second, 20 meters per second, which means you're covering more ground. And if you're to graph that on a position time graph, you're going to get a quadratic. You're going to see this in the lab. So this is coming. We're just kind of hitting everything as an overview. And then the ticker tape questions. Don't let those, I don't want to say this. Don't overthink them. So picture yourself in a car and I mean, you shouldn't toss stuff out of a car, but let's just say you're in a car and you're tossing out pennies. If you were going at a constant speed, there'd always be a right. Every penny would fall evenly spaced. As long as you're going at a constant speed, you have a penny, 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 right? If you're speeding up, then the pennies are going to start to get closer together. And so on a ticker tape diagram, they're going to be bunched up. If you That's if you're slowing down. Hopefully, I don't know if I said that. If you're slowing down, they're going to get closer together, right? As you get slower, and you're putting a penny every second. So every 1 second, you're putting a penny, but your speed's decreasing, so they're going to bunch. They're going to bunch up. Sorry, guys, my brain wants to say it backwards. If you're speeding up, then you're going to put a penny down every second. But if you're speeding up, you're going faster, so you're covering more ground, so the pennies are going to spread out. And then, so just you'll see a couple questions at some point with the ticker tapes. And I think that is the end, guys. Desmos review quiz. You guys, we're not, we may or may not do quizzes. You will definitely do the reviews. And that'll happen after the unit. So I'll do this real quick. Definitely read the directions. They're kind of based after the Wordle, the Wordle game, but they're multiple choice. So you'll have 8 questions. Um, and you'll go through all 8 and answer them, and then you'll hit check answers. And then what it'll do, it'll either say they're all good and give you a green little check mark, or they'll say something is wrong. But it doesn't tell you, right? Wordle doesn't always tell you where the letter goes. Like, so it's got to give you it tells you the letter's right, but it doesn't tell you where it goes. So this is kind of the same idea. I didn't make this up. I made up the questions, but the guy who made up this game is not me. But anyway, the first time you do it, it's a little annoying because you don't know which 8 are wrong, which is the whole point. It is meant for you to go back and look at the questions multiple times to like make your brain process stuff. And so the second time, so then you go to the next slide. It'll say try again on the next slide. So you go to the next slide, and now, same 8 questions. You're going to answer the same 8 questions again, but this time you're going to look like you know something's wrong. For all you know, they're all wrong, or it's just one that's wrong. So this is why it's a little annoying. But again, it's made to make you think and process and question yourself and all that fun stuff. Your brain should be a little confused and thinking. That's good. That means you're learning something. But the second time you do it now, and I don't remember the order of the numbers. I think let's just say it gives you the even. It does 1 through, so it gives you it checks the 4 even ones and it checks the 4 odd ones. And let's just say if we got the 4 even ones right, it'll put a green check. And then by the 4 odd ones, it'll say, "Hey, try these again. One of these, at least one of these is wrong. Could be all 4, could be 1, 2, 3. You get the idea." And it says go to the next slide. So then you go to the next slide. Now it's going to tell you 1 through 4 and 5 through 8. You'll see it'll make more sense when you're doing it. But each time you go to a slide, it's going to give you more details. So it's giving you hints without just giving you the answer like Edpuzzle and all that other stuff we do or quizzes. So it just makes you think a little more, which is good. On that note, when you get all green checks, just stop. You don't have to keep answering. It's the same questions for all 7 slides. You don't necessarily have to do all 7 slides. If you get to the very end, at the very end, then it's individually going to tell you if it's right or wrong for each question. But if you get them all right before that, you don't have to keep going. And then problems, we're going to do some classic problems, quizzes problems. The Desmos, the review, that was what I was just talking about. Factor of change method is a sorry, guys, this is the last thing. is something I will talk about on one of the digital board problem slides. Uh, I'll walk you through it real quick. So there are questions where it'll say you're driving down the road at X meters per second. How much further would you go if you were to double your acceleration? So it doesn't really give you numbers, it just gives you factors, double, triple, half, that kind of thing. And then I'll show you those on the class cake. But those are so they're you kind of treat them like you're solving a problem, but it's more a conceptual question. But there's a math way to solve it. The conceptual way, some people can do it. I can't. I'm not one of those people. I like to see it written out, and then, so I will show you my little. I hate calling it a shortcut, but it's a little shortcut that gets us where we need to be. All right, guys.